This is Unit 1, Topic E. We're going to continue to find limits analytically, meaning we have to justify our limits using algebra. But unlike the last section, this time we're going to look at x as it approaches infinite values, positive infinity or negative infinity. First of all, just a reminder, if we take the limit as x goes to infinity, and our result is a finite number L, what we really have is a horizontal asymptote. Same idea if x approaches negative infinity. If the result is finite, we get a horizontal asymptote. This is end behavior. We've seen this a little bit in the past, but just a reminder that the horizontal asymptote doesn't necessarily have to be the same on both sides. We may have one side a different value than the other, or even a horizontal asymptote on one side with the other side going off to infinity or negative infinity. When there is a horizontal asymptote, the value of the limit gives essentially the equation of the asymptote. All right, let's start thinking about what we'll need to consider to do algebraic limits as x goes to plus or minus infinity. I'd like to start by just thinking about rational functions. Remember, those are the p of x over q of x functions, one polynomial divided by another. As we start to think about those, there are a few basic strategies that we'll need to keep in mind. And I'm going to start out with the ones that basically they're just common sense. If a quantity becomes infinitely large in the positive direction, we say it approaches infinity. And if it becomes infinitely large in the negative direction, we say it approaches negative infinity. If we have a finite number divided by something that becomes infinitely large, either way, positive or negative direction, let's think about what we have. We have some constant, some finite number over something infinitely large, or possibly some constant finite number over something infinitely large but in the negative direction. Think through an example of this in your head for a moment. Just pick a constant, let's say 5. And then think of a really huge number on the bottom. 5 divided by 1,000,000, 5 divided by 1,000,000,000, 5 divided by 1,000,000,000,000. Those tiny, tiny fractions are getting closer and closer to 0. Of course, it would work the same way here. We would just take 5 divided by negative 1,000,000 or negative 1,000,000,000 or negative 1,000,000,000, and they're still going to be really tiny fractions, just slightly less than 0 and approaching 0. So either way, if I've got some finite number on the top divided by something infinitely large on the bottom, that fraction is going to approach 0. That idea is actually what we need to fill in this little box at the bottom of the page. If I have some constant, which I'm now calling k on top, and x to any power on the bottom, as x goes to infinity, this basically becomes k over infinity and goes to 0. If x is approaching negative infinity, same idea. Depending on the power, right, whether it's even or odd, the bottom could be positive or negative infinity. Can't say for sure unless we have more information. But either way, a constant divided by something infinitely large is going to go to 0. You can really see that in the graphs of these functions. If n happens to be even, all of these functions look basically alike. If I just pull up a quick Desmos graph here, and we go ahead and do, say, just pick a constant, doesn't matter, 5 over x squared, or 5 over x to the 4th, or 5 over x to the 6th. Right? They all essentially look the same. They just get a little bit steeper the higher the power. In this case, you'll notice we've got a limit of 0 over here on the left end at asymptote at 0, and the end behavior on the right end also goes to 0. So we're seeing that limit in the graph that we were just talking about. Right? So if n is even, the graphs all look like this. And these limits, these end behaviors, can be clearly seen in the horizontal asymptotes at the ends. If I just change these to odd powers, first power, oops, I guess I gotta put a first power in there, or a third power, or a fifth power. Once again, the graphs all essentially look the same. They just get a little steeper the higher the power. But once again, if you look at the end behavior, these graphs are approaching y equals 0 on the ends, which is an illustration of those limits that we just talked about. So if n is odd, the graphs just look like this. But we continue to see the end behavior near 0, justifying those limits graphically. All right. Let's also talk about just powers of x. Looking at the graph of x to the n power, if n is even, so we're looking at things like x squared, x to the 4th, x to the 6th. You've probably seen enough of these by now to know that they all basically look like this. The classic parabola for x squared. X to the 4th and x to the 6th, again, just get a bit steeper. And you'll notice that the end behavior on those, whether we're going to positive or negative infinity, goes up to positive infinity. And that makes sense, right? If it's an even number, it doesn't matter whether we start with a positive or a negative. An even power is going to result in a positive limit. If n is odd, these all kind of look alike. Again, they all look kind of like the x cubed graph. X cubed, x to the 5th, x to the 7th, and so on. Once again, they get a bit steeper with the higher powers, but they all look somewhat alike. And the end behavior here actually does go up to the right towards positive infinity. Because of the odd power, it's going to go down to the left towards negative infinity. And again, it makes sense. A positive number to any power is positive, but if I take a negative number to an odd power, I'll get a negative result. All right, we will take the sets of limits in those two boxes that we just filled out kind of as givens, things that we can use anytime we need them. And we're now ready to tackle some rational functions. So, generally speaking with a rational function, when we first plug in our value, we can't really plug in infinity, but we can imagine it anyway. We generally get an indeterminate form of the form infinity over infinity. To actually find the limit, we're going to use the same technique every time. We'll divide the numerator and denominator by the highest power of x in the original denominator. That's going to give us a form that's going to allow us to analyze using these ideas that we just finished developing. So, taking a look here. If x goes to infinity, first of all, you'll just notice if x is infinitely large, that's going to be infinitely large, and so is that. So we do get the indeterminate form, infinity over infinity. It tells us we need to do some algebra. The algebra I'm going to do is exactly what we're touting here as our cure for this problem. So let's do it. I'm going to divide both the numerator and the denominator by the highest power of x in the original denominator, which in this case would be the x squared. I'm going to write this first one out really carefully, and then after this, if you want to take some shortcuts, we can. But I'm literally dividing every single term by that x squared. All right, let's simplify that. That'll just become 3 plus 5 over x to the first minus 2 over x squared. And on the bottom, we've got 2 minus 1 over x plus 4 over x squared. Now remember what happens to all of these fractions that have a finite number on the top and an x that's approaching infinity on the bottom. This is like 5 over infinity. That goes to 0. 2 divided by something really, really large, 2 over infinity, approaches 0. 1 over infinity approaches 0. 4 over infinity approaches 0. All of those fractions go to 0 in the limit. And so all we end up with is the 3 over 2. So what this is telling me is the limit we did is the one where x is going to the positive infinity. So we're now saying that on the right-hand side, there's a horizontal asymptote at y equals 3/2. Okay. Technically speaking, this would have come out the exact same even if x had been going to negative infinity. All of these fractions would have still gone to 0. So that's true for the left side as well, but I'm only going to write down the conclusion for the specific limit that we did, which in this case was the positive infinity or right-hand side. All right, let's try a couple more of those. In number 2, we once again have a rational function. X is approaching negative infinity. And notice that that would become infinitely large here. That would go to negative infinity, technically. So I have infinity over negative infinity, which is still an indeterminate form. So I'm going to follow the little technique. I'm going to look at the denominator and pick the highest power of x in that denominator. In this case, x cubed. And let's divide everything, top and bottom. So I'm dividing by a form of 1, right? Divide by x cubed. I'm going to show you what I usually do here, and you can decide how much you need to write out to make yourself comfortable. I usually do most of the division in my head, so I don't have to write quite so much out like I did up here. I write out the fact that I'm dividing by this form of 1, so my reader, right, for you guys, that'll be me. My reader knows what I'm doing, but then I just divide mentally. So 3x squared divided by x cubed is 3 over x, minus 6 divided by x cubed. And on the bottom, those x cubes would cancel out, and I would get a 4, plus 5 over x squared, plus 1 over x cubed. So again, if you can do the algebra in your head, as long as you've documented what you're going to do, feel free to take that shortcut. If it's easier for you to write it all out to make sure you don't make mistakes, that's fine too, of course. All right, let's see what we've got here. 3 over negative infinity, that goes to 0. Minus 6 over negative infinity also goes to 0. On the bottom, I've got 4. Same argument, plus 0, plus 0, right? All of these fractions are finite numbers over something that's getting infinitely large or infinitely small. That gives me 0 over 4, or 0. Notice it's really important that I didn't have 0 on the bottom. That would have been indeterminate, right? But 0 divided by any other number other than 0 gives me 0. by always dividing by the highest power of x in the denominator, you actually do that to prevent ending up with all zeros on the bottom. So as long as you follow that protocol, you'll be fine. All right, so the end behavior this time, and this would be the left end, we would have a horizontal asymptote at y equals 0. All right, let's do one more. Let's see here. This time we want x to go to negative infinity again. And I can see already that if I tried my substitution method, this would become a negative infinity on top. And that's squared, so it would actually become a positive infinity on the bottom. So there's my indeterminate form again. And so we'll use our technique. We'll divide through by the highest power of x in the denominator. In this case, the x squared. So I'm dividing by the form of 1, x squared over x squared. All right, so what have I got this time? That's going to give me x to the first minus just 2 plus 2 over x squared. Bottom's just going to be 2. So this time, I still have an x in here. As x goes to infinity, I'm just going to kind of write that x as negative infinity. Then I'd subtract 2, plus that fraction will go to 0, 2 divided by an infinitely large number, over 2. Now technically you can't really do arithmetic with infinity. We write this here more as a memory aid than anything else. But if I have negative infinity and I add or subtract anything to it, it's still negative infinity. And if I have negative infinity and I divide it by 2, it's still negative infinity. So my limit this time is negative infinity. That means my end behavior on the left goes down. All right, some of these limits may remind you of some shortcuts that you probably learned somewhere in a college algebra or pre-calculus class. I'm going to remind you of them and just say that now, instead of just being told these are rules, we actually have the math to back them up. Most often, college algebra and pre-calc classes teach that in a rational expression, if the degree of p is smaller than the degree of q, then you end up with a horizontal asymptote on the x-axis, y equals 0. What that is saying to us now is that the limit is 0. Notice that for us, that happened right here. The degree on the top was smaller than the degree on the bottom, and we ended up with 0 as a limit. If the degree of p is equal to the degree of q, that was our very first example here. The degrees were both 2. Then notice that the solution, the limit, was just the ratio of these leading coefficients, the 3 and the 2. So if the degrees are equal, the limit going to either positive or negative infinity is the ratio of the leading coefficients. Finally, the last example that we did, if the degree of p is greater than the degree of q, like it was up here, degree up here was bigger than the one down there, then your limit's going to be infinite. It will be either positive or negative depending on the specifics of the situation, but it will be either positive or negative infinity. Right. Let's go ahead and just use some shortcuts to determine these limits quite quickly now. So here I want x to go to infinity, and I'm going to notice that the degree of the top is bigger than the degree of the bottom. Because I'm going to positive infinity, I don't even have to worry about it. The limit is going to be positive infinity. In number 5, the limit is going to negative infinity, but I'll notice that the degrees are the same. So my limit is the ratio of the leading coefficients. That would really be 1 over 3. And I guess I forgot on this one, I'll go back and do it. This one would say the end behavior on the right goes up. And this one, because it had a finite limit, said on the left, there's a horizontal asymptote at a third. All right, coming down here. This time, my larger power is on the bottom, so the degree of p is less than the degree of q, meaning the limit's going to be 0. We're going to infinity, so this is on the right. We have a horizontal asymptote at y equals 0. And finally, on this last one, we're going to negative infinity. So the limit's either plus or minus infinity. And I have to be a little bit careful here to determine the actual sign of my infinite answer. Use the first terms. X to the 5th divided by x squared would be x cubed. So this is going to behave like x cubed. If I take a negative number and cube it, I'll still get a negative answer. So this one is going to go to negative infinity. Had that been, say, x to the 6th over x squared, it would have behaved like x to the 4th. And with an even power, I would have gotten a positive infinity. So make sure you take into account what the exponent would behave like when you decide positive versus negative. So this one's going to be to the left and down for the end behavior. All right, we'll pause there and we'll come back and look at some examples of functions that aren't rational functions in the next part of this video.